In this video, we will estimate the square root of 99.6 using a linear approximation. And we will do this by choosing a function f of x and a reference point, and then by using the tangent line, the linear approximation L of x, and through differentials. These are all linear approximations. Now, a good choice for f of x is the square root of x, as we're trying to calculate the square root of 99.6, so the square root function is a natural choice. Now, what we need is a reference point, and a reference point is a point close to where we want to know the answer, where we actually know the answer exactly, and that's when x is 100, since 100 is close to 99.6, and we know the exact value of f of x there, namely 10. We choose 100, f of 100, which is the point 110, as our reference point. First, we use the tangent line. The slope of the tangent line is given by f prime of x, and we evaluate that at the point of tangency. So if f of x is x to the 1/2, f prime of x is 1/2 x to the minus 1/2, which is 1 over 2 x to the 1/2. When you plug in 100, you get 1 over 2 times the square root of 100 over 10, which is 0.05. Now we just plug into point slope. Y minus y naught is m, which is f prime of x minus x naught, and we get y minus 10 equals 0.05, the slope we calculated, times x minus 100. Our approximation is the y value when x is 99.6, so y minus 10 is 0.05 times 99.6 minus 100, and doing the algebra, we end up getting 9.98. In actuality, to 5 decimal places, the square root of 99.6 is 9.97998. So you can see this is a very good estimate. It's only off by 2 in the 5th decimal place. Okay, now we're going to do this using the linear approximation L of x, which is pretty much the same thing we just did, because L of x uses the tangent line to approximate the function. So we write down the tangent line again, y minus y naught equals f prime of x naught, x minus x naught. You move the y naught onto the right-hand side, and you've got y equals f prime of x naught times x minus x naught plus y naught, which is L of x. So to get our approximation, we plug in 99.6, and the calculation looks exactly the way it did before, and we again end up with 9.98. Now we're going to do differentials, which in the beginning will look somewhat different. So our function y is x to the 1/2, so dy dx is 1/2 x to the minus 1/2, which is 1 over 2 x to the 1/2. And thus dy is 1 over 2 x to the 1/2 dx. Now here we're going to think of dy and dx as changes in y and x along the tangent line from our reference point. So using 110 as the point of tangency, dy is y minus 10, and dx is x minus 100. And when we plug in, we get y minus 10 is 1 over 2 times 100 to the 1/2, x minus 100, which is the equation of the tangent line again. So when you plug in, you get 9.98.